So now, starting the exercises about complex numbers with something quite simple first. The first thing you do, of course, if you introduce complex numbers is you try and find out how to perform the usual calculations like addition, subtraction, multiplication, and so on. Also division and even to potentiate complex numbers. So that's a little bit not in a special order here, as you can see, but anyway, to save some space, I'll just start right here. And then if something is, if you need explanation or you don't get it, just give me a hint, because otherwise I try to save a little bit of time. If you look at this example here, it strikes you that this could be done by use of the third binomial formula. That's a good idea. Like the scheme that you know is a plus b and then multiplied by a minus b. And we all know that the result is always equal to a squared minus b squared. So that seems, and don't ask, is it valid for complex numbers also? The answer is always yes. There is no reason to use a different set of rules for doing arithmetics on complex numbers. The only specialty with complex numbers is as soon as I or j pops up, or yes, it comes into play, it must be treated accordingly because it's special. Yes, its specialty is exactly that its square must always be -1. That's all we need. And of course, all we've been doing with numbers so far should be valid furthermore. The idea by introducing complex numbers is not to find something totally different, but to find a generalization of things we've been doing with numbers all the time. Yeah? So that's a very good attitude towards complex numbers. Now, in this case, of course, I must identify this A of our scheme with the number 2 and B with this J, this special, this imaginary unit J. So that's why I can say that 2 plus J times 2 minus J is directly speaking 2 squared, 4, minus J squared. And since J squared is always identical to -1, minus gets plus, then the result must be 4 plus 1, which is equal to 5. Also, this is exactly speaking a special case which is worth noting, because generally, and I can write in general, in general, it holds that complex number z multiplied by its complex conjugate, as you know, denoted with this star, this asterisk as a suffix. This is the so-called in German we say Betragsquadrat. You would say the absolute value squared. With complex numbers, the so-called absolute value is also called the modulus. Okay, so but that's a fact, and this is exactly what we've been doing here, because you see that this number is the complex conjugate of that one. So that's actually taking the modulus of this number, you find it's square root of 5, and also for this number, and then the product of these must be 5. So that's no surprise. Okay, then I don't know which order. I take this one next. So I just add these two numbers to each other, and that's also an important result. It means that if you add two numbers that are complex conjugates to each other, that the imaginary parts cancel. So the result is purely real. In this case, it's always greater than or equal to 0. So it's not negative, non-negative. In this case, it's real. It can be negative, but not no imaginary part. It's clear 2 plus 2 is 4, and j minus j cancels. So that's easy. It has to do with the geometric effect when building the complex conjugate. As you all know, it's like you take the mirror, with respect to the real axis, to the horizontal axis. Okay, you make an axis mirror. Anyway, I don't know, some of them you may do yourselves. I just brutally put this away to save some time. Let's take this next. It's a division, and this is one of the reasons why we introduced the complex conjugate, to be able to bring to make a division in such a way that we have Cartesian form in the end. So what do we have to do? One good idea is to expand in a certain way this fraction. I don't know, is that the correct term to say expand? So what I do is I multiply the numerator and the denominator with the same term. In this case, I take the complex conjugate of the denominator, right? So that always means j must be replaced by minus j. That's the best way in all the cases to build the complex conjugate. You could also say I changed the sign at the imaginary part, but a better method is to replace j by minus j, because then it also works for polar form, exponential form, and others. That's just a recommendation now. So if I do this, I know what happens. It's always the same effect. In the denominator, I get, again, it's like third binomial formula, or like I said before, it's the square of the modulus. So it's just the square sum of the components. That's what it is, right? So we have 3 square down there, plus, always plus, yeah? It's due to the j square effect. So plus 4 square. In this case, that's the Egyptian triple, as it's called sometimes, the Pythagorean. You know that the sum of these squares is also a square. And anyway, we remain 3 plus 4j in the numerator. So all we get is, here down here, I have 9 plus 16 is 25. So I can say it's 1/25 times, and then 3 plus 4j. So that you could say that's already Cartesian form. Yeah, of course, this factor belongs to both, but it's nicer to put it this way than to draw it inside the parentheses. That should be correct. If you get something different, just tell me. So now this is a case where it's quite interesting to compare the arithmetic method of evaluating with the geometrical method. You may know that I'm a huge fan, a huge supporter of graphical solutions. And this is such a nice example, because you can draw it and then you can see how easy it really is if you have understood what it means to potentiate complex numbers. As you remember, the potentiation takes place only with the modulus, while the argument of this number is actually multiplied by this exponent number. So it's the argument as an angle, you know, the direction angle, is just taken times 6, which is a very interesting effect when using complex numbers. So the graphical viewpoint, I'll try to make a little sketch here, would be roughly speaking like I have, you know that what I could do here is I could break it out factor 1/2, and you will shortly see why I'm doing this. No, but that's no, that's wrong. I wanted to draw factor 2 outside, and so now it's 2 times inside is 1/2 plus square root of 3/2 times j. Why am I doing this? Do you have an idea? So it seems that you just made the calculation and did not really think about what you're doing there, probably.
Yeah, I
Because
think
it's
the polar form.
Pardon?
Is that the polar form?
No, not really. Yes, something like it goes in that direction. Yes, actually, it's something which tells me what the argument is. I mean, I could use the polar form and then sine and cosine as you know it, yeah. But
Yeah,
what I want to do, I
do
want
that.
to find out without calculating which direction it is, and that's what I wanted to show you with this little sketch. I'll try. Okay.
Yeah.
If I take the units circle, first of all, this is a unit number. You know what I mean with unit number? It means that the modulus is 1. So it as a vector, it lies on the unit circle. Why does it? Because the square sum of the components is 1. You see it? 1/2 squared is 1/4. This one squared is 3/4, and 1/4 plus 3/4 is 4/4. So it's equal to 1. Yeah. So that was the trick. But I saw that these are very well-known values of sine and cosine. So I make a jump just for a second, a jump to the other exercise later. This one, this so-called help table, I wanted to recommend you because it's very easy to remember if you once got it. It's to remember the values for sine, cosine, and even tangents if you want. So you must remember to use the following angles, like 0, 30, 0 degrees, 30 degrees, 60 degrees, 90 degrees in steps of 30 degrees. But in between, also don't forget the 45 degrees. This is what you do. By the way, this is the natural measure for angles called the arc measure. It's much better. It's the mathematically correct measure, but in the engineering field, we're still used to. It's just still what people do is they use these degree. This degree notation. You can do it, but you should also know how to get from here to there. So you know that pi, the number pi, refers to the 180 degrees, to the straight angle. It's also called. Okay, so that means if I take pi third, I must take 180 by 3, and this results to 60 degrees. So that's not really hard to change from here to there. Anyway, now the values of sine can be memorized, but with the following trick. The trick is you take 1/2 times root of number. So 1/2 times root of 0 is this. 1/2 times root 1 is 1/2. 1/2 times root 2, 1/2 times root 3, 1/2 times root 4. You understand what I mean? So this is what this is just a, how do you say in English? It's a Eselsbrücke, a Merkhilfe. It's a trick to remember these numbers. When I say this is 1/2 times square root of 4, this is just to remember it. But the square root of 4 is 2, so 1/2 times 2 is 1. There's no question, yeah? So this goes 1/2 root of 0, 1/2 root of 1, 1/2 root of 2, 1/2 root of 3, 1/2 root of 4. It's very easy to remember. And also the values for cosine are much the same, but backwards. Exactly the same values backward. And then tangent, okay, of course, that's also easy because it's the, you know what it is? It's the division of sine by cosine. So I have 0 by 1 is 0. 1/2 by square root 3/2. I can simplify to 1 by square root 3. Then I can put it to this form also, root 3 by 3. Anyway, here I have the same values for sine and cosine. You see here, this is the curve for sine and cosine, and where they intersect, this corresponds to the 45 degree, to the P4th angle. So they are same values, same by same equals 1, and so on. For tangent of 60 degrees, square root of 3, tangent of right angle, P1/2, is not even defined because 1 by 0. Yeah, so that just for your orientation to remember. And that's what I'm using here. Let's look again. So the cosine of 30 degrees is, no, other way around. The cosine of 60 degrees is 1/2. Also here, but I'm looking here, 1/2. And the sine of 60 degrees, on the other hand, is 1/2 times square root of 3. What does it mean? This is our coefficient, this is our component of our complex number for the real part, and this is for the imaginary part. Always the cosine and the sine. It is the polar form. That's what I was doing when I extracted the number, the factor of 2 back to here. Okay, so I could easily see that this is nothing else but, let's do it this way, 2 times, and this inside here. Now I jump to the exponential form even, because this is even more compact, you know it, right? E to the j times that angle. P, what did we say? P third, which means 60 degrees. I'm quite convinced that this is the number that we have, and this should be taken. This should be taken to the power of 6. Now, here inside, so it would look a little bit like this, perhaps a little steeper, like this. You know what I mean? So that real part would be 1/2, and imaginary part like root 3 by 2. This is near to 1. It's just a very, very rough sketch that I'm making here, just to show you how you can roughly obtain a graphical solution and then do the calculation more exactly. You know, the calculation is good for exact results. The graphical solution is good to get an orientation of what you have. What I'm talking about is that I have the unit circle around here. And if you are familiar with geometry of circle and then the connection to sine and cosine, you know what it's all about. Second. Roughly speaking, that's what I wanted to transport to you. Okay, you can guess that this is exactly in the middle between the center and the this outer line of this unit circle, and this one is near to the 1. So it's plausible. It's plausible for this argument phi to be 60 degrees, or say p third. That's what I'm using here, and just without doing any calculation, and then I can easily say now the power to the power of 6. This whole expression means, of course, it means 2 power 6 times now, and this is by the 5th law of potentiation, which has nothing to do with complex numbers directly, but by Euler's formula, this is a valid identity that the imaginary exponential term represents the same thing as the polar form and the Cartesian form. And that's why it represents perfectly the fact that when you potentiate a complex number, that its argument is taken times this exponent, because by the fifth law, you know, the fifth law of potentiation, which is valid in general, it says a to the b to the c, this way, is the same as a to the b times c. So a to the power of, you can take these exponents and multiply them. And that's what I'm doing here. So 6p third, if I reduce to lowest number, 6p third, what do I get? I think it is, isn't it 2 pi? 6 pi third, it's 2 pi, isn't it? And that's funny. Why is that funny? What would you say? What is this number? It must be a unit number with a direction and an argument of 2 pi, which is the full angle. Tell me, which number is this? You're not yet so familiar with.
60.
But this is 360 degrees, of course, yeah. But we don't need the degree measure. What we need is to know where in which direction does it show if it has a full angle here. You know, you go to the right and then you turn around and make a full turn, and then
It is parallel to x-axis.
Right. It's parallel to the x-axis and it shows to the right. So
Right.
and it's a unit number. So it's nothing else than the number 1. It's exactly 1. That's another way to write down the 1. Actually, it is. And that means the result is 2 to the 6, which we all know is 64, right? Yeah. Positive real number. That's the result for this expression. The lady, I don't know how many ladies there are, but the lady that was talking just before, and she said she already, and also many of the others, I hope, have all done this. Did anybody do this calculation by hand or by binomial formula? That would be nice also. Pascal's.
Yeah, I used binomial. I
Okay, did you get the same result? Real 64?
I have the same result by hand.
Yeah, that's nice, because you see how simple it is. What I'm doing is actually I take this number as a how do you say, Zeiger, the arm of a clock. Do you say arm? I think so, yes, as an arm. And then I rotate it to the sixfold value of its argument, you know? The argument is 60 degrees. I take this times 6, I get 360 degrees, and it lands here. It lands here alone. And that's the number 1, positive real. But of course, before I do this, I have separated the factor of 2, and that's why the 2 to the 6, of course, takes place here. Okay, so this is just an aspect of what's happening here. This is the argument thing that you can see here. What happens to the argument? What happens with the direction? The rotation of a complex number by potentiating this. This is what you see here. If you think about rotating it. But the modulus aspect is inside the calculation. So, or I can say, or you would say 1 plus root 3 times j to the 6. It's like Pascal's triangles. That would really be the best idea then, if you know what I mean. This is for binomial formulas as we know them. This is the next step to the power of 3. For the power of 4, I get 1, 4, 6, 4, 1, and then you know I get 1, 5, 10, 10, 5, 1. So still another, it's not enough, right? Is that power of 5? And then I need 1, 6, 15, 20, 15, 6, 1. That would be the coefficients of, did anybody put the brackets there and then again, and really multiply it? That's possible, but that's at least as much effort as using the binomial coefficients for that case. You know what I mean? What I mean is I would have to take one by, let me see, by that scheme, 1 by 6 plus 6 times. Now I go here, you know, 6 times 1 by 5 and times root 3j. That's like a to the 5 times b to the 1, the scheme of binomial formulae in higher, with higher exponents. And then I would get plus 15 times 1 by 4 times j, no, not j square, times, you know what I mean, and so on. But I don't want to do this in detail. Root 3 times j, but
Square.
squared, right, and so on. But it's much work, you know. Plus 15. Oh no, 20 is missing, right?
Yeah.
Plus 20 times 1 power 3, and so on. You can do it. It's a good training, but it's much work. Plus point. Okay, dot. I think that's enough for this part. Looking at the clock, that's the most important cases done. So if I put this away, I don't mean leave it away just for now. I cross it out so that you know we don't talk about these, but it's not hard to do anyway.